AI/ML model, breakdown of the Sankey diagram depicted in the video, focusing on its components and what it represents in the context of auto high-end engine parts production. Pradeep K. Suri, author, researcher, and AI/ML architect. Overall structure and purpose. Sankey diagrams are a type of flow diagram used to visualize the magnitude of flow between different nodes in a system. The width of the links, the connections between nodes, is proportional to the flow quantity. In this context, the diagram illustrates the flow of materials and processes in the manufacturing of auto high-end engine parts. Key nodes and their interpretation. Engine parts, red. This is the starting point. It represents the initial raw materials or components required to begin the engine parts manufacturing process. The thickness of the outflow indicates the total volume of engine parts entering the system. Stock check 1, yellow. A quality control or inventory checkpoint immediately after the initial engine parts input. It assesses the quantity and quality of the parts. WIP, work in progress, pink. This represents the parts currently being processed or assembled but not yet completed. It's a measure of inventory within the production process. Subassembly 1, green, and subassembly 2, blue. These are intermediate stages where individual engine parts are combined to form subassemblies. The flow from stock check 1 leads into subassembly 1. There is a connection between subassembly 1 and subassembly 2. Stock check 2, yellow. A point where the subassemblies or components are checked for quality or are inventoried again. Assembly line A, orange, represents one of the assembly lines where the engine parts and subassemblies are further processed and assembled. Assembly line B, purple, represents another distinct assembly line. PO, purchase order, gray. This node video represents the stage where a purchase order is initiated. This node looks like it starts near assembly line A and then proceeds to QC, quality control. Stock check 3, yellow. Another stock or quality check video occurring closer to the final product stage. QC, quality control, orange. A critical stage where assembled components undergo rigorous quality checks before being dispatched. Client feedback, indigo/dark purple, represents the feedback loop from customers regarding the engine parts, contributing to process improvement. Dispatch, orange. This node follows assembly line B, represents the engine parts and subassemblies are prepared for dispatching. Flow interpretation. The thickness of the gray streams connecting the nodes visually represents the quantity of parts moving between each stage. Thicker streams indicate a larger flow. Notice how the engine parts stream splits. Some flow goes to stock check 1 and from there towards subassembly 1. Another stream goes towards WIP. This suggests that some parts might be undergoing a different, parallel process. The assembly line A stream eventually goes toward QC while the assembly line B stream eventually heads to dispatch. The width changes in the streams reflect losses, example due to quality failures, diversions, example to different assembly lines, or combinations of flows. In summary, this Sankey diagram provides a high-level visual overview of the engine parts manufacturing process, highlighting the major stages, flow quantities, and key control points such as stock checks, quality control, and feedback loops. It is a valuable tool for understanding overall efficiency and identifying potential bottlenecks in the production process. Sankey diagrams can be surprisingly useful in AI modeling, especially when you're dealing with complex systems or trying to visualize data flows within algorithms. Here's a breakdown of how they can be advantageous. 1. Visualizing data flow and transformations. Model architecture. In complex neural networks, especially those with branching or merging paths, a Sankey diagram can illustrate how data moves through the different layers. Nodes represent layers, and the flow width represents the amount of data passing between them. This helps understand which layers contribute most to the final output. Data pre-processing pipelines show how raw data is transformed through various pre-processing steps: cleaning, normalization, feature extraction, etc. The diagram can highlight which pre-processing stages have the greatest impact on the data volume. Generative models: in models like GANs, generative adversarial networks, a Sankey diagram can visualize the flow of information between the generator and discriminator, revealing how the adversarial process shapes the generated data. 2. Understanding feature importance and relationships. Feature selection: visualize the flow of features through a selection process. Starting with all features, the Sankey can show which features are retained at each stage of the selection algorithm. Decision trees and random forests: while not a perfect fit, you could represent the flow of data through different branches of a decision tree using a simplified Sankey. The node widths would represent the number of samples taking each path. 3. Identifying bottlenecks and inefficiencies. Resource allocation: in AI systems that manage resources, example computational power, memory, a Sankey diagram can visualize how these resources are distributed across different tasks. This can help identify bottlenecks where resources are concentrated, leading to delays or underutilization. Error propagation: although more complex, you could potentially use a Sankey diagram to visualize how errors or uncertainties propagate through a model. Node widths could represent the magnitude of the error at each stage. 4. Explaining AI decision-making. Attention mechanisms: in NLP models, attention mechanisms assign weights to different parts of an input sequence. A Sankey diagram could visualize how attention flows from input words to output predictions, highlighting which input elements are most influential in the final decision. This helps make the model's reasoning more transparent. Explainable AI: XAI Sankey diagrams can visually summarize the output of XAI techniques, such as SHAP values, by illustrating the contribution of different features to the model's prediction. 5. Monitoring and debugging AI systems. Data quality: track the flow of data from various sources and visualize how data quality metrics, example completeness, accuracy, change as the data passes through different stages of the AI pipeline. Model performance: monitor the flow of predictions through different performance categories, example true positives, false positives, to identify areas where the model struggles. Caveats. Complexity: Sankey diagrams can become cluttered and difficult to interpret if there are too many nodes or connections. Simplification and abstraction are often necessary. Quantitative accuracy: while they show relative magnitudes well, they may not be suitable for precise quantitative analysis. Not universal solution: Sankey diagrams are best suited for visualizing flow-like processes. They are not appropriate for all AI modeling tasks. In summary, Sankey diagrams offer a powerful way to visualize complex data flows, relationships, and processes within AI models. By providing a high-level overview, they can aid in understanding, debugging, and explaining AI decision-making. Thank you.